And you are going to be asked to determine what symmetry it has. Now, there are all kinds of things that things can be symmetric about. So think of a parabola. Do you remember last year when you studied parabolas, you found the axis of symmetry? And it was like the line y equals 7, or x equals 7, or x equals -3, right? It was something like that. So you can have those kind of individual symmetries. The main symmetries that we kind of want to analyze for all of our curves are these. These are the main ones. Now, we've already talked about the x-axis and y-axis. Who remembers the test of symmetry for the x-axis? You have an equation. Change the sign on y. So for the x-axis, we change the sign on y. And remember, when you do that, the equation that you end up with, so you go through and you make all your y's negative, and then you clean it all up, and it has to end up exactly the same as the original. By the way, you can memorize this certainly if you want, but if you think about it for a second, if something has symmetry about the y-axis, doesn't that mean this point has a sister point right here? So if this one is 2, 4, this one has to be -2, 4. So doesn't the sign on, oh wait, I was doing x-axis, sorry. All right, let's do this one. So if it has symmetry about the x-axis, this would be the point 2, -4. So around the x-axis, the y sign changes. Around the y-axis, the x sign changes. It makes so much sense. We change the sign on x. Now, any ideas how we might test for symmetry about the origin? Now think about what the origin, where the origin is. And if you're symmetric about the origin, then this little point right here would end up being reflected over here. So what happens when we do that?
You make the y and x negative?
We make both of them negative, so we change the sign on both, exactly. When you have a curve that you have determined is symmetric about the origin, it is called odd. An odd function is symmetric about the origin. Remember, an even function is symmetric about the y-axis. Okay? Now, just as a little, I know we've talked a little bit about this, soon we're going to be talking about our BFFs, our basic family of functions. The classic even and odd functions, this is your sine curve. Part of it. I mean, it goes on forever and ever. That is considered odd. Do you see why? See what happens here? The cosine curve, on the other hand, is considered even. You see why it's considered even? It has symmetry about the y-axis. So in trigonometry, there are 6 functions, you know, sine, cosine, tangent, secant, cosecant, cotangent. It's important as we graph them to know if they are even or odd. So main 2 are sine and cosine. Sine is odd, cosine is even. Okay. All right, and finally, the line y equals x. Now, the line y equals x is called the identity line, right? Because y and x are the same. Points are 1, 1, 2, 2, 3, 3, 4, 4, right? Any idea, if I took a point, like let's say 2, 1, and I reflected him across this line, any idea what point that would become, Mr. Fahey?
1, 2.
Bingo. So what's our test for symmetry about the identity line? What happens to x and y? They switch. So you switch x and y. Okay? Everybody okay with that? All right, so those are the tests. So now what we're going to do is test a couple of them. So we're going to check y equals 3x squared plus 5, and we're going to figure out which of these symmetries it has. You guys are smart. You can probably do most of these in your head, but I'm gonna write it all out since this is our first one. We're gonna see what kind of symmetry this has. So I'm gonna test the origin, I'll put them in the same order here. The identity line, the x-axis, and the y-axis. So I'm just gonna do the test for each one. So for the origin, I'm gonna change the sign on both. Remember, if you simplify this, it needs to come out to match the original if it has symmetry, okay? Is this going to simplify to what I started with? No, this one's gonna go away, right? And that one has to be divided over. I do not get the same equation. So this is a no. The identity line, I simply switch my x's and y's. That one is an obvious no, would you agree? X-axis, what's that test again? What's the test for the x-axis? Change the sign on y. So, I don't think it has symmetry, do you?
No.
And then the y-axis, how about this one, no? I think that one does, doesn't it? Now, some of you smarty pants knew that from the start, because what shape is that? It's a parabola. Where's its vertex?
Y-axis.
Yeah, 0, 5. So if you have a parabola, vertex at 0, 5, isn't it symmetric about the y-axis? Yeah. We're just doing this for practice. Let's do one more equation, and then we'll talk about the asymptotes. All right, one more equation. Anybody know what shape this is? This is a crazy looking equation. Anybody know what shape it is?
It's like the cosine or one of the signs.
It is not. No. This is what we call a hyperbola. Do you know what a hyperbola is? A hyperbola is a shape, and it can be configured anyway. This particular one is configured sideways like this. It can also be up and down. It can also be diagonally done. That's what we've got. So we're talking about this in terms of symmetry, but this is not a function, right? Not a function. And my picture kind of tells you what we have symmetry about. But that's okay. Let's test it. How about the origin? What do I do to test for the origin? Change the sign on x and y. Well, wait a second. Is that going to give me the same equation?
Mm-hmm.
Yes, because the negatives are going to get squared out. Okay, what about the line y equals x? I'm going to switch the variables. Now be careful. You might think that's the same equation, but is it? No, that is not the same equation. This hyperbola would be oriented up and down. It's a different equation. So that's a no. This one was a yes. X-axis, change the sign on, go back to the original. So x squared equals negative y squared plus 8. Do we have a match? Yep. And then y-axis. I think we have another match, don't we? So this one has symmetry about everything except the identity. Okay, you got the hang of it, folks? So you're gonna learn your test of symmetry. All right. Okay, now we got a discussion about asymptotes. Okay, there's all that formal stuff there where asymptotes, horizontal asymptotes are limits. Okay, they're limits. We're gonna talk about what that means in a second, and we're gonna use the appropriate notation. We are calculus students, so we're gonna use the appropriate notation. I know They don't always use it in Algebra 2, but we're gonna make sure we do. So, we've got a picture in 8A, we're gonna talk about asymptotes using this kind of picture. And it looks like I have a horizontal asymptote at y equals 2. It also looks like I have a vertical asymptote at x equals 0. So, do you understand that an asymptote is a line that the curve approaches? Actually, it doesn't even have to be a line, but for us it will be. A line that the curve approaches but doesn't intersect. So the farther you go, the closer you get, but you never get there. That's called a limit. The farther we go, the closer we get, but we never get there. So, when we talk about end behavior, we're talking about what the curve is doing as it goes off the end of the page. So, I'm going to look over here on the right side of my picture, and I'm going to talk about the limit as x approaches infinity. Now, that means I'm going that way. Would you agree? That's where x is infinity. And I want to know what happens to y. Remember, this is the same as y. So as x goes to infinity, what is my y doing? It is decreasing, right? But not forever and ever. Doesn't it have like something stopping it here? So we say the limit is 2, because that's the lower limit, right? But then we put a little plus sign here, because the curve can approach 2 from the top, which is what the plus means, or from the bottom, in which case I'd put a negative. The whole purpose of this notation is to tell somebody who wants to know what this picture looks like without having the picture. When I see this notation, I know that whatever's going on in the middle, as we go all the way to the right, the curve is coming down closer to 2 from the top. On the other side, as we approach negative infinity, this is called end behavior notation. As we're approaching negative infinity, what's happening to the curve?
Getting closer to 2.
It's getting closer to 2 from the bottom. That's right. So that plus and minus have nothing to do with positive and negative. This means you're coming in from the top. This means you're coming in from the bottom. This is called the end behavior of that curve. Okay? All right, let's look at the next one. Can you describe this end behavior? Well, this one looks different. All right, so can you tell me what's happening to my y values as my curve goes to the right? The farther I go to the right, what is happening to my y values? It's coming down, getting closer to 0. So I will say that 0 from the top. And on this side, remember this is my end behavior notation. It always looks like this. As I'm approaching negative infinity, so what are my y's doing? Same thing. So I never want you to think that your one-sided limits, your limits on each side, I don't want you to ever think that they can't be the same. They can be. Just depends what your picture looks like.
Is 0 plus basically saying that the line, it will, or like the y value will always be above 0?
Yep. On that side, yep. Mm-hmm.
So our limit is only dependent on our horizontal asymptote?
No. So one of the things, right now, we're just talking about end behavior. So end behavior is going to be an asymptote because end behavior describes what the curve does as it goes off the page, and there's going to be an asymptote somewhere. Or If it's shooting up into space, then we say there isn't that, or we put infinity here, if there's no limit to stop it. You can talk about limits right here, but they wouldn't have this notation, because this notation applies to the ends of the number line. Positive infinity all the way out that way, negative infinity all the way out there. If I wanted to talk about this right here, what's going on, I would say the limit as x approaches 0 from the right, because now I'm talking about what happens as I approach 0. Well, what happens to my y as x approaches 0 from the right? My y's are going, I'm trying to say infinity. And then what happens as I approach 0 from the left? That's also positive. So you can use limit notation anywhere on your picture. But in terms of end behavior, it's always approaching infinity and approaching negative infinity. But anytime you have an asymptote, or really anything, you can talk about the limit. All right, now the rubber meets the road, because now we're gonna look at a function and we're gonna talk about all the stuff we've talked about the last couple of days. And we're gonna see if we can put it all together. So, I am going to rely on you remembering something from last year. Mr. Miller indicated that you guys have spent some time with this. So look at that long list of stuff. There's A through G we have to answer. So domain asymptotes. By the way, the word asymptote, when you write it, has a P, but when you say it, it doesn't have a P. Right? Reminds me of one of my favorite shirts of all time. Back when we had IB math here, I taught it way back like 2009 or something. And great group of kids, had it for 2 years. IB math was a 2-year class. Great group of kids. So they were helping me design the math road shirts that year. And they came up with this great t-shirt. And of course they all have to be approved, and admin said no. So we were devastated, but came up with another shirt and whatever. Last day of school, they come in, they hand me this bag. They had made these illegal t-shirts, and they all were wearing them, and they gave me one. When I had a room downstairs, I had it hanging on the wall. It was so cute. On the front, they're black, big white letters on the front. Got math, you know, like the old got milk thing. Got math. On the back it said, "You bet your asymptotes." Isn't that cute? I thought it was adorable. All right, anyway, so our job is to figure out all this stuff. There's a whole bunch of it. We gotta figure it all out. And I think it's gonna be much easier if we look at a picture. So, tell me what you know about this thing. Maureen.
You know that x could not equal -3.
Bingo. So since you're restricting x, you're talking about a domain thing.
Yeah.
And you're saying it can't be 3 or -3. So it can be anything except -3. Would you agree with that? So I will use my interval notation basically just to describe this on the number line. Everything except -3. When you tell me x cannot be something, that is a vertical asymptote. So we are going to have a vertical asymptote at x equals -3. Let me say that again. Vertical asymptotes are cannot be's. So the minute you say x can't be this, that's a vertical asymptote. You can have more than one vertical asymptote, depending on how much stuff you have in your denominator. Vertical asymptotes come from the denominator, because isn't that where the cannot be's come from? Yes. Very good, Maureen, thank you. That helps a lot to get us started. Okay, is there anything else you know about this picture? Anything, whether it's in the list or not, anything. Oliver?
I think I remembered if you get the coefficients of the x values, like 2 over 1, then it would be a y limit or something.
Horizontal asymptote. It is the limit of the function, but the limit of the function is going to be graphed as a horizontal asymptote. Now, for those of you, very good, Oliver, very, very good. Your teacher should be commended. That's awesome. And you should be commended for remembering. What he's saying is, if you think about end behavior, and end behavior is a limit as x approaches infinity or negative infinity, that's what end behavior is, period. No confusion. That's end behavior. He says, okay, if x is going to infinity, what kind of a number is it? Isn't it big? Like 1 billion? Well, think about this problem if you put in x equals 1 billion. The top would be 2 billion minus 1, and the bottom would be 1 billion plus 3. These aren't important, right? When we're talking about billions, those two numbers aren't important. So what is our limit? 2 billion over 1 billion is 2. So that's your horizontal asymptote. Your horizontal asymptote comes from doing exactly what Oliver said, comparing the power, the x's. Now, to extend that, if your problem is bigger than this, you compare the highest power. So if you had something like x squared plus 5x minus 8 over 3x squared minus 2x plus 9, if you had something like that, this is where you would look. You look at the highest power. Because again, when you're talking billions and trillions, this is where the power is in the problem. I mean, this is the big numbers right here. The rest of it's important, but fizzles away as you get x get bigger and bigger. Okay, now, that's very good. That alone, though, does not help us fill this totally in. Tess?
The powers, would that?
The what?
The powers, if it was like x squared or 3x squared, would the horizontal be 2?
2/3. If it's 2x squared over 3x squared, and then more stuff, the asymptote would be at 2/3. You compare the power, the highest power.
What if it's like 2x like cubed over 3x squared?
Oh, well then we have a problem, don't we? But you can figure it out, because if it's 2x cubed, over 3x squared, your job is to do what Oliver said. We're gonna compare the highest powers, okay? Now, what's the highest power in that problem? 3?
Yeah.
Well, I got 2 of those on the top. How many do I have on the bottom?
No.
So I'm gonna write 1 in. My job is to compare the highest powers, and if I'm missing something, I gotta put it in, so 0. So what have I got now?
0.
2 over 0. 2 over 0. What's that? Doesn't exist? So this thing does not have a horizontal asymptote. It does have an end behavior asymptote, and that's a discussion for another day, because that's a lesson that we need to do. But it does not have a horizontal asymptote. And Tess, if you think about it, that makes sense. Because in your example, think of x being 1 billion. On the top, I have 2 times 1 billion cubed. Oh, that's really big. On the bottom, I have 3 times 1 billion squared. That is also very big. But compared to each other, isn't this a whole lot bigger than the bottom? And so your fraction isn't coming toward anything, it's just getting bigger and bigger and bigger. If I graphed this, it would be shooting off into space. Not a straight line, it would be some kind of weird shape, but it's shooting off into space. It is going to be following some kind of asymptote, and we'll figure out what that is at another time. For now, our end behavior is gonna be horizontal. Okay, but you're right, great questions, good thinking, Lauren.
So right now, we don't need to worry about like exponents in the x or
Yeah, you do, but they'll match.
Okay.
Because as long as they match, your asymptote's horizontal. Okay? Alright, okay, back to the action here. We gotta get going on this, we wanna get this problem done. I wanna get this one completely done. Alright, so what's my dilemma? I'm ready to fill this in. I know these are twos, but what do I not know? Which way it's coming. So I gotta kinda get a handle on this. Alright? So what if I said to you, let's let x be 0. Just go back to your equation. What happens if you let x be 0?
Negative 1/3.
You get negative 1/3. So maybe like right here, the point 0, negative 1/3. Would you agree with that, Lucy?
I have a question. I'm confused on the limits. So why are they both 2?
Because this gives me my horizontal asymptote. There's one horizontal asymptote.
Oh, okay.
Can't have more than one. Unless you got some weird radical or something in a split, but we're gonna have one horizontal asymptote. Okay. Now, for me, quit watching the clock, Tess, you're gonna get out here soon enough. For me, that's enough. Because I've done a million of these. You've done a few. Does it make sense to you that this looks something like this? And what's the other half of the picture look like? Diagonally opposite it? Now, I'm 63. I've been doing this for 42 years, okay? That is automatic for me. It might not be automatic for you. So what are you going to do? You need to get a picture in front of your face so that you can answer these questions. How did I even get started? I let x be 0. Could I let x be 1 and 2 and negative 5 and negative 12? So if you ever are unsure about what your picture looks like, plot some points. Just plot a few points, right? And if you're doing homework, I don't care if you type it in on your calculator to get a picture of it, but be able to do it without the calculator if called upon to do so, like I just did. Okay? Now I can answer some of these questions. What's the limit as x approaches positive infinity? 2 from the bottom. And as x approaches negative infinity, 2 from the top. What is the range of this? Now remember, domain involves the x's, right? We already cleared that up. What is our range? Everything except 2. The range is everything except 2. Why isn't it 2? We got an asymptote there, and does the curve ever touch it? No. Kids, if I took these away, could y be 2? Y would be 2 if I took those away, right?
Yeah.
But when I add and subtract these things in, this will never equal 2. You understand that? That cannot equal 2 because I've added and subtracted to those values. Okay, we're gonna finish this problem. Here we go. We've done domain, asymptotes, range, and behavior. Continuity. All right, so I have my picture in front of me. Yesterday we talked about continuity, meaning if you're continuous, that means what?
You can
I can draw my whole picture without lifting my pencil. All right, so let's start over here on the left. Uh-oh, can I draw the whole picture without lifting my pencil?
no.
No. So this is not continuous. I need you to describe the discontinuity. So it's not continuous. because it has what?
Infinite
And
discontinuity.
you can either use your book language and infinite discontinuity. I like the term non-removable, but I don't care. Either one, non-removable or infinite discontinuity where? At x equals -3. You have a complete and total break in your problem at x equals -3. Okay, Marin?
Wouldn't it also be at, y equals 2?
No, continuity is draw your picture left to right. So continuity involves x's. What causes me to lift my pencil? Y has nothing to do with it. What causes me to lift my pencil is I run into that asymptote. That has nothing to do, that doesn't make me lift my pencil,
Okay.
right? Continuity is left to right. So is increasing and decreasing. We're looking at x values left to right.
What's the curve on the?
I can't hear you, Tess, you're gonna have to talk louder.
What's the curve on the, like, negative 30, like, by that? Are we not working with that at all?
Does anybody know what I can't even hear. What did you say?
The upper left curve, why is it the upper left curve? Like, why is it like that?
Why is it like this?
Yeah,
Yeah.
why is it like that?
Okay, well, plot a point. What's -4? If I put -4 into my graph,
It would be
I get -9 over -1. So at -4, my y value is 9. I just got done saying, Tess, I know what these look like, cause I just do it. You don't? Okay, so what do? Plot points. When I put in -4, I got 9.
So that gives me two different lines, or like curves.
The curve is broken at -3. You have to have something on the left of it and something on the right of it. Oh, I meant that backwards. You gotta have something on either side, okay? The only time you won't is when your domain says, I have 2 pieces to my domain. So I'm gonna have 2 pieces to this graph. I have to graph each domain piece. All right, you gotta get through increasing or decreasing. Now, this is moving left to right. Okay? What is happening to my pencil as I'm moving left to right? What's going on here?
it's going up.
It's increasing. So it is definitely increasing on the interval from -infinity to -3. Does everybody agree with that?
Yeah.
Okay. Now, what about over here? What's my pencil doing over here? It's also going up. So this is increasing on its entire domain. Would you agree with that? Now, usually somebody's gonna say, but that arrow's going down. Stop. We're moving left to right. And as I move left to right, my pencil is only going up. It doesn't have any decreasing intervals. This one doesn't have any. Certainly it's possible to have both. You don't. And then extrema. Okay, who remembers how I described this extrema yesterday? What are extrema, Liam?
Isn't it the tops of hills and the bottoms of
It
hills?
is. So it's relative high points and low points. So when you're sketching, you got some weird thing like this or whatever. This is a relative high point. Compared to the points on either side, that's a high point. This would be a low point compared to the points on either side. I want you to look at this picture. With that particular shape, are there any relative high points and low points? No. This one has no extrema. No extrema. Now, somebody might say, but Mrs. Ford, there's an absolute maximum. Here, this thing's shooting up to infinity. Yes, but that isn't considered an extrema because we don't have any hills and valleys.
Wouldn't the wouldn't it also be increasing up to like y equals 2?
That's why we put this on here. This is from here to all the way, just going up.
Oh,
Okay, guys, you gotta get comfortable with this kind of notation. We're gonna do one more of these next time, and then we're gonna move on. Okay, excuse me.
Was that where you got off?